Hello everyone, I am Savinay Nagendra. I am a PhD candidate in the Department of Computer Science and Engineering at the Pennsylvania State University. It is my honor to present our work, PatchRefineNet, improving binary segmentation by incorporating signals from optimal patchwise binarization, which has been accepted as a poster in the WACV 2024. The outline of today's presentation is as follows. First, I will be introducing the problem. This will be followed by the motivation. Next, we will be discussing the proposed method. After that, we will be discussing the experimental setup. And finally, we will be discussing the results. So let us start with the problem introduction. What is binary segmentation? The purpose of binary segmentation models is to determine which pixels belong to an object of interest. For example, consider this aerial image. Here, let us say the task in hand is to determine which pixels in this image are part of roads. For this image is given to a segmentation network, which is typically an encoder-decoder architecture. And this network predicts this logic map. So a logic map is nothing but a map of logic scores. That is, the segmentation network assigns a logic score, that is a probability score, to each pixel. And these are converted into predictions by thresholding. That is, each pixel with a logic score greater than or equal to tau is predicted to be part of a road. And this tau is a fixed value, which is typically taken to be 0.5 for binary segmentation. And this will result in the final binarized predictions. So what is the problem in the way we perform binary segmentation? Well, a common phenomenon in current and former state-of-the-art segmentation models is spatial bias. What is spatial bias? Well, in some patches, the logic scores are consistently biased upwards, and in others, they are consistently biased downwards. These biases cause false positives and false negatives in the final predictions when thresholded by a fixed value such as 0.5. Consider this logic map from a state-of-the-art model called COANet, which is used for road segmentation from satellite images. The regions marked by pink boxes represent image patches with significant downward biases in their logic scores. In these patches, the pixels that belong to road have an average logic score of 0.2. Meanwhile, the cyan boxes represent image patches with significant upward biases in their logic scores, where the average logic scores in cyan boxes is about 0.7. Well, now you see what the problem is. Having significant amounts of non-road pixels with higher logic scores than actual road pixels is problematic, because binarization, that is the task of thresholding with a fixed value, will produce final predictions with many false negatives in the pink boxes and many false positives in the cyan boxes, which will ultimately affect the performance of the segmentation network in terms of its mean intersection over union. And this type of spatial biases in logic maps is not specific to only COANet, but it is a consistent trend for all segmentation networks that we have tried. To study the effect of spatial biases and for interpretability, we can divide the image into k distinct patches uniformly. And we can observe a spatial bias trend in these boxes. For example, in the boxes that are marked pink, we can observe there is a downward spatial bias trend, and in all the boxes that are marked cyan, there is an upward spatial bias trend. That means the pink boxes will ultimately, after binarization, contain false negatives, and the cyan boxes would contain false positives, which would affect the mean intersection over union. So what is the goal of our method? The goal is to correct patch-wise spatial biases that will reduce the overall false positives and false negatives in final binarized predictions, thereby increasing segmentation performance. So how do we design a method to handle spatial biases? Well, clearly, to handle spatial biases, the logic maps in different image patches should be handled differently. What would be a naive approach? We can allow each logic patch to have its own threshold and have a neural network trained to predict what this patch-specific threshold should be. For example, if the neural network believes that the logics are biased upward in an image patch, it can set a higher threshold for that patch. Right? Instead of having a fixed value of binarization for the entire image, we can have different threshold values for each patch. Well, what would be a problem with such an approach? An important shortcoming of this approach would be that it's too rigid, right? As it does not take care of spatial variation in the bias inside each patch. So what is the spatial variation? Inside an image patch, there could be spatial variation in the bias. For example, in an image patch that is generally biased upwards, there will be many clusters of pixels with upwardly biased logic scores, but there can still be clusters with downward biases or almost no biases. Binarizing such a patch with single threshold can often result in clusters of false positives and false negatives. So, so what's the approach? A better way could be that we can have a neural network learn the patch-wise spatial biases of a base segmentation network and then adjust the logic score of each pixel to compensate. Right? So instead of handling thresholds of each patch, we can actually learn the spatial bias of each pixel in a patch, and then we can adjust the logic score of those pixels to compensate. Before heading further, it is necessary to answer an important question, which is why don't existing segmentation networks automatically correct their own biases by training with ground truth? Well, we conjecture that during their training, the loss is at a pixel-only level, right? And the loss depends on the label and prediction for the pixel. That means that the neural networks are not very good at noticing general trends in their errors for clusters of pixels. So we need to have a separate signal apart from the ground truth that reflects collective trends and biases in different patches. So this brings to our proposed method, which is called the PatchRefineNet or the PRN. So input to PRN is the logic map produced by the base segmentation network. PRN learns the spatial biases of the base network and adjusts the logic score of each pixel to compensate. PRN uses two learning signals during training. So as we discussed previously, PRN would require two learning signals. The first one would be the ground truth labeling of each pixel. The second is a novel learning signal from a set of pseudo labels. So what is this novel learning signal? So the novel learning signal is designed as follows. For each image patch in a training image, one first finds an optimal threshold for binarizing that patch. Then one uses these patch-specific thresholds to binarize each patch. The resulting binarization of each pixel is the pseudo label for that pixel. Intuitively, pseudo labels train PRN to detect the overall bias in a patch, while the ground truth learning signal trains PRN to detect exceptions. For example, clusters of pixels with downward bias inside a patch that is generally upward biased. Typically, networks that are designed for post-processing have two branches, a global and a local branch, and we follow the same network design. So the global branch helps PRN understand the relationships between the patches, right? Which means that a PRN takes the features from the bottleneck. The global branch of PRN takes features from the bottleneck and it upsamples like any general encoder-decoder architecture. But there is also a local branch, which basically goes into the intra patch. That means it basically analyzes each patch or processes individual patches to learn about local properties or biases in that patch. So logic map produced by the base segmentation network is resized to 512 cross 512 and given as input to PRN encoder. The output of the encoder is a feature map with 1/8 the resolution scaling. This is simultaneously passed through the global and local decoder branches. The global decoder takes the entire feature map at the bottleneck as input. Before running the local branch, the feature map at the bottleneck is split into k disjoint patches, where k is equal to 512 divided the patch size parameter p, the whole square. Right? So the patch size parameter p is a hyperparameter that we are going to see how it's fixed, right? In the next slide. Each patch is independently sent through the local branch to produce 1/k of the logic map, and the full logic map is then reassembled from these pieces. So before going further, it is very important to answer why do we train PRN separately from the base network? If a train-based network already exists, example, a state-of-the-art from the prior work, this reduces resource consumption compared to retraining everything from scratch. Another reason would be once the base network is fixed, its logic map for each training image won't change. Hence, PRN can avoid expensive recomputation of the pseudo-labels it needs. And finally, learning signal from novel pseudo-labels used by PRN does not have a meaningful derivative with respect to the weights of the base network. So let us now come to the ablation experiments. Ordinarily, the base model would train on the training set and tune hyperparameters on the validation set. However, PRN uses the validation set because this is where the spatial bias of the base models becomes apparent. This raises a very important question of whether it is a fair setup. That is, would it be better to simply add the validation data to the base model's training set and not use PRN? To answer this question, we consider the following three cases. Case A is where the base network trains on the training data and tunes hyperparameters on validation data and PRN is not used. Case B is where the base network is trained using the combined training data and the validation data and PRN is not used. And case C is where the base network trains on the training data and tunes on the hyperparameters on the validation data and PRN is used, which is our case. As we can see, reserving some data for hyperparameter tuning is beneficial to the base network where case A improves upon case B. And reusing this validation data to train PRN shows a further significant boost, which means case C is by far the best. This validates our proposed setup for how different parts of the data are used. Coming to the hyperparameter, which is the patch size parameter P. As the patch size parameter P decreases, the number of patches that the PRN's local decoder has to process increases exponentially. This means that the local decoder is able to process each patch's information in a more focused way as the patch size decreases and the number of patches increases. But after a certain point, that is at a saturation point where p equal to 64, what happens is that the local decoder does not have enough information to process as the patch size becomes very, very small. So we choose p to be 64 in all our experiments, which results in the highest MIOU. So we show results on two binary segmentation datasets, which are, of course, public benchmarks. We can see that there is a significant difference with and without PRN, and we experiment with different networks, and we see that addition of PRN to all the networks has a significant increase in the MIOU, especially if you observe the last rows for both the Deep Blue and the KVAS IR-seg datasets. We observe that there is a 2.7 and a 2.3% improvement over the current state-of-the-art models after using PRN, which is a significant improvement. We also extend PRN to saliency detection, and it can be seen that PRN has a significant increase in MIOU on the DUTS saliency detection dataset. We also show that PRN can be extended to few-shot segmentation, and PRN again has a significant increase over the current state-of-the-art models. So the key contributions of our work is as follows. PatchRefineNet, or PRN, is a post-processing network that sits on top of a base binary segmentation model and learns to correct its spatial biases. PRN uses a novel learning signal that is computed from binarizing each patch separately and optimally. PRN complements virtually any binary segmentation network. In our experiments, across different state-of-the-art base models and across different datasets, PRN consistently improves segmentation performance by 2 to 3% in MIOU over the base networks. PRN is also shown to be better refinement scheme and more memory efficient when compared to other post-processing schemes. More results for this have been shown in the paper. Thank you. Please visit us at Poster 1 session on January 4th, 2024 from 8 p.m. to 9:45 p.m.